Well, it's the science and the engineering of materials that are used in everyday living, but also high-tech new materials. It reminds me of a book written by Professor Steve Sass from Cornell University, and he wrote a book called The Stuff of Civilization. And he traced the history of civilization, and every time humanity invented a new material, there was a big leap and a jump forward for the whole of civilization. So there was the Stone Age and the Bronze Age, and then the Iron Age, and then the Steel Age. And with each new technology, civilization made huge leaps and jumps forward. And we're still making significant leaps and jumps forward, like the internet and all these electronic gadgets. It changes the civilization and culture significantly. Ceramic is a refractory, non-metallic material. The refractory means it's high temperature. It's high temperature, and there are books about. It's called the hidden technology because it is an enabling technology. Because it's so high temperature, you can pour molten steel in, molten metals into it, and it enables other technologies because it contains them. There's a lot of good physics and chemistry waiting to be discovered in ceramics. Ceramics is still the Wild West. You can still be a one-man band or a one-woman band. In physics, high-energy physics, when you write papers, you have about 24 authors. But here is still, you can make significant contributions because it's still an undiscovered field of research in terms of solid-state physics and chemistry. Ceramics itself is a traditional field. Archaeologists use it a lot. But nowadays it's ripe for a lot of physics and chemistry studies. Because it's got vast resources available to it. I left Berkeley and it wasn't easy. It's not exactly the Riviera, but it's the MRL Materials Research Lab is a national resource centre, and it's got a lot of really good equipment that's just as good as Berkeley or Stanford, better in many ways, and the cost of living is not so high here. It's got a lot of good resources, and it's got a lot of faculty in other engineering departments with whom you can collaborate and write big proposals. Well, our research focuses on science and engineering of ceramics and ceramic composites. We do basic science, plus we do engineering. What we do is invent new materials. Then we think of something to do with them. So we go out and find new science that nobody knew before. We use the synchrotron up at Argonne National Lab, at Brookhaven National Lab. We had to invent a little furnace that goes to 2,000 cm air because aeroplane engines don't work in a vacuum, they work in air. So you've got to study ceramics at high temperature in air. And we find new phase transformations, how to change crystal structures as you heat them. And then we use those to make ceramics that don't break so easily, especially at 1600 cm air. That's one of our research areas. Another area is geopolymers, which is a relatively new up-and-coming area. It's a potential solution to global warming in that it can replace Portland cement, and Portland cement, to make it, liberates 1 ton of CO2 into the atmosphere, whereas the geopolymers or inorganic polysilate polymers liberate only 0.2 tonnes of CO2. The resulting material is 3 times as strong in compression and 2 times as strong in flexion. Well, actually 2 times as strong in flexion and 3 times as strong in compression, and sets to full strength in one day. And so we can make a lot of composites. This material does not need to be fired. Normally, to make a ceramic, you have to heat it 1500 C, 1, 2, 3 hours. But this ceramic, you get a powder, which is a clay, and a paste, which is like a sodium metasilicate, and you mix them up and you pour them into a plastic mold, and they set. And it looks like a ceramic, feels like a ceramic, breaks like a ceramic, but you didn't even have to fire it. And so that's opening a whole, instead of plastics, there's a whole new inorganic polymers. And a lot of people are getting quite interested in it. And then we do other research for the Army, inventing new concepts for stress wave mitigation. That means how to dissipate the energy of an incoming blast, a ballistic impact. And then we've got other research topics. I just worked really hard, and then I came to Berkeley, and they asked me to lecture a class because Professor Fulrath died suddenly because he smoked cigarettes. Don't do that. And he died within 6 weeks, and so they needed somebody to teach, and so I was asked to teach, and I thought it was a pretty good activity, and so I just kept on going. It's an enabling technology. It's all pervasive in our culture and in our lifestyle. It ties a lot of other disciplines together: mechanics, physics, chemistry, electronics. These are real materials based on the science we know separately. And material science is a good field. Even the College of Engineering knows it's a good field. They let us concentrate on research. I think we're number 2 in the country now. We were number 1, but MIT wrote a book, so now we're number 2. So we got to write a book and get back to number 1. But it's a good program here. Material science in general ties a lot of physics, chemistry, maths, and electronics and mechanics together. Also, in the past, students come from high school and the highest GPA go to physics and then chemistry and sort of some of the leftover GPA students sort of meander into material science. But when you go out to industry, it's the material scientists people that tie together the physicists and the chemists and the mechanicians. And so they're like an orchestra conductor. And so it's not a bad way to go.